Okay, let us get started. Today we come to the last chapter of our course to be devoted to symmetry in quantum mechanics. The notion of symmetry is fundamental to whole physics, and quantum mechanics is no exception. On the contrary, it provides an ideal playground for applying and exemplifying most of abstract mathematical concepts you have learned in your course on group theory. So let us write down the title. So, chapter 10, Symmetry in quantum mechanics. And the first question that we'll consider is symmetry and conservation laws. Yes, please. As I have told you, you may put on your earphones and go into Russian channel. You should mute, choose Russian channel, please. Symmetry and conservation laws. Symmetry and conservation laws. Well, let me start with a brief reminder of the notion of symmetry in classical mechanics. In Hamiltonian formalism, we define a classical system by specifying its Hamiltonian, right? Just a function on the phase space of a system. So let me divide the whiteboard into two parts. Classical mechanics. So in classical mechanics, we start with a Hamiltonian as a function of the canonical variables Q and P. That is a set of position coordinates, generalized coordinates Qi and the conjugate momenta J. These are supposed to satisfy the canonical Poisson bracket relations. And now by symmetry transformation, or just symmetry, we understand any canonical transformation of the phase space that lives invariant the Hamiltonian. What does it mean? So we consider a coordinate change from lowercase qp to the new coordinates. Let me denote them by q capital and p capital. So that the new coordinates q and p satisfy the same canonical Poisson bracket relation. They have the same fundamental Poisson bracket, that is Q with Q is equal to 0, PR with PG is equal to 0, and QI with PG is given by the Kroneker's delta IJ. And we also require this canonical transformation to leave the Hamiltonian unchanged. That is H of Q and P capital is equal to the H of Q and P lowercase. A large class of canonical transformations is given by the so-called point canonical transformations. That's what we call the notion of point canonical transformations. Point canonical transformations. These have the following form. Q capital is given by Q capital of Q. P J is given by some matrix J of Q times G, where G, J, I is given by dq by dq ij to the minus 1. As a seen, point canonical transformations are for point canonical transformations, the new generalized coordinates q are functions of the old ones, right? And the new generalized momenta p are given by linear combinations of the old one. So doing the matrix of linear combination is just the inverse to the Jacobi matrix of the coordinate change in the configuration space. So we conclude that each point canonical transformation defines and is defined by an arbitrary coordinate change in the configuration space of the system. And as you know from classical mechanics, this point canonical transformation will leave the Hamiltonian intact if and only if its coordinate space part preserves the Lagrangian of the system. That is, L of Q dot is equal to L Q dot small plus total derivative. So we preserve the Lagrangian of the total derivative. Then the full transformations will preserve the Hamiltonian. Now let's turn to quantum mechanics. In quantum mechanics, we describe the states of a quantum mechanical system by vectors of a complex Hilbert space. And to specify dynamics, we need to choose an energy operator called Hamiltonian or quantum Hamiltonian. Now, by definition, by a symmetry transformation in quantum mechanics, we understand every unitary transformation in the Hilbert space of states that leaves invariant the Hamiltonian. So let me write down this sentence in formulas. Quantum mechanics. So we consider a unitary transformation in the Hilbert space. Each unitary transformation takes each ket vector psi into a new ket vector, that's denoted psi prime, the Hilbert space of states. Unitarity implies that the inner product of psi1 with psi2 is equal to psi1 prime, psi2 prime. And invariance of the Hamiltonian under this unitary transform implies that making a sandwich are from the Hamiltonian and the transformation operator, we get the initial Hamiltonian. That's our definition. And the characteristic property of unitary transformations is that they preserve the inner product in the Hilbert space. In physical terms, we can also say that unitary transformations preserve the transition amplitudes between any pair of states. As a consequence...
Can I pose a question?
Yes?
Can we consider the unitary transformation as transformation that preserves the length of...
Yeah, you're right, exactly. We can define a unitary transformation as a transformation which preserves the length or norm of all vectors in our Hilbert space. These definitions are equivalent. If we insist on preservation of length, then we can deduce these transformation also preserve arbitrary inner products and vice versa. Okay, as a consequence of this property, we conclude that each unitary transformation preserves probabilities of transitions between the states. So just taking absolute values, we find that P12, the probability of transition from state psi1 to psi2, given by psi1 psi2 squared, is equal to psi1 psi2 prime squared. And the last equality looks quite natural. If we think of symmetries as those transformations that map any pair of states, psi1, psi2, to an equivalent pair of states. As usual, by equivalent states, we understand the states which are physically equivalent to each other, possess the same properties, physical properties. And in particular symmetry transformations can't change probabilities of transitions because these values are measured in experiments, and so they must be the same for equivalent states. Conversely, if we start with some linear operator U that preserves all inner products, or what is the same, which preserves the probabilities of transitions, then we can deduce that this operator is unitary. So acquiring this, we can deduce that the operator is unitary. Another property of symmetries that can be seen from the definition is that physical equivalent states, that is, states related by a symmetry transformation, evolve with time to physical equivalent states. Indeed, it follows immediately from the invariance of the Hamiltonian that the symmetry operator U commutes with the Hamiltonian. We just multiply this expression by U on the right and get that U commutated with H is equal to 0. So any symmetry operator is integral of motion. Its total time derivative in the Heisenberg picture is equal to 0. But we should keep in mind that U is a unitary operator. It is not a Hermitian operator, so we can't associate it a physical observable. Anyway, it resolves with time. Then for a time-independent Hamiltonian, we have the following evolution operator. U of t is given by exponential of th. Clearly, this evolution operator, being a function of our Hamiltonian h, also commutes with the Hamiltonian, right? It's commutes with the Hamiltonian and with our symmetry operator, right? So U of t commutes with the symmetry operator U. Let's now take a pair of physical equivalent states at some time moment, say t equals 0. Psi prime and psi naught. So So we suppose that this, at some time moment, some instant of time, t equals 0, these states are physically equivalent, that is, related by some symmetry transformation, U. Then I claim they will be equivalent for all times. Let us prove this. So we can write that R psi prime at the moment t is given by the action of the evolution operator on the initial state, psi prime 0, and using this quality we can write this as action of the symmetry operator of the state psi. Now, using the fact that evolution operator commutes with a symmetry operator, we can write this as u of t phi 0. And this combination gives us psi at the moment t. So we get u acting on psi of t. Right? So we see if two states happen to be equivalent at some instant, then they stay equivalent for all times. We can also rephrase this statement by saying that our time evolution is invariant. Time evolution is invariant under symmetry transformations, or symmetry transformations preserve time evolution. Any questions? Comments? No questions? Don't hesitate.
Thanks.
Maybe in Russian. No questions? Okay. Let's go ahead. Now let us denote by G of H the set of all symmetry transformations associated to a given Hamiltonian H. All symmetries of the Hamiltonian H.
It's not quantum case.
Yeah, now we are discussing only quantum case. That's why I put head on H. Now it is not hard to see that this set, G sub H, is actually a group with respect to the operator composition. What we can take as a unit of this group? Do you have any idea? Identity operator, right. Because identity operator is clearly unitary. Yeah? It preserves the length of the vector. And it is also clear that identity operator commutes with any operator, in particular our Hamiltonian H. So we have a unit as a symmetry operator. Unit operator is a symmetry operator. Then to each symmetry operator we can associate its inverse operator, right? And in view of unitarity, we can also write it as an adjoint of U, or Hermitian conjugate. Is it clear that the inverse operator also preserves the Hamiltonian? How to see this? It follows immediately from the definition. We can just multiply this identity with equality on the right to u to the minus 1 power, and on the left and on the right to u, written in this form. And then we get h on the left and h times u to the minus power and to the minus power to the minus power on the right, which means that this operator preserves the Hamiltonian. So, to any symmetry operator here, the inverse is also a symmetry. It's also a symmetry of the Hamiltonian.
Excuse me. We speak about groups on a unitary operator.
So we consider as a group of unitary operator, special unitary operator, that preserves our Hamiltonian. First of all, any symmetry is a unitary operator. And among all possible unitary operators, we pick up those which preserve our Hamiltonian. Okay. It remains to check that the product of two unitary operators from our set G sub H is closed with respect to the. It is also a symmetry. So this set is closed with respect to the operator product. So suppose we have a symmetry U1 and a symmetry U2, and we consider the product of these two operators, and making the sandwich of U and H. We already defined that because of the associativity of the operator product, we can write this as U1, U2, H, U2, dagger, U1, and since U2 is a symmetry by assumption, we can continue as U1, H, U1, with the heads, and again, U1 is also symmetry, so we get our Hamiltonian, and that is our Hamiltonian. And so the general conclusion is that the product of U1 and U2 is also in the group G sub H. So G sub H is a group.
Крест, у крест, он называется?
Oh, dagger, you mean? It is not cross, it is dagger. Dagger. Usually defining the whole group, identifying the whole group of, finding the full group of a given Hamiltonian may be a challenging problem even for simple quantum mechanical systems. In practice, one considers only some suitable subgroups of this full group, which are immediately related to the problem under consideration. If we now think of this subgroup G as an abstract algebraic group, then they assign to each of its element J a unitary operator in the Hilbert space defines a unitary representation of this group G in the Hilbert space of states of a given quantum mechanical system. So we can always think of these unitary operators as defining a representation of some abstract group G in the Hilbert space of states.
Can I ask a question? I don't
Yes,
understand this notation because G is also a unitary operator.
No, G is an element of abstract algebraic group.
An abstract algebraic group is subgroup of GH.
Yeah.
And G is also a group of unitary operators.
Yes, there is some cycle of ideas. After we establish the fact that our symmetries form a group, we can forget about the origin of this group. We can think of this group as an abstract algebraic object.
Okay.
Suppose we have some set of transformations that leaves a Hamiltonian invariant, and then we have a representation, a unitary representation of these symmetry transformations in the global space of our states, of states of our system. In general, this unitary representation is neither faithful nor irreducible. So in general, it is a reducible representation. Now, to whet your appetite for symmetries, let us consider a few specific examples. And as a first example, example 1, let us take a system of n identical fermions. The states of such a multi-particle system can be described by wave functions depending on xi 1, xi n, where each xi refers to a complete set of variables associated to a given fermion. This may be position coordinates, spin variables, or something else. Since the identical particles are completely indistinguishable in quantum mechanics, as you know, any permutations of these particles must be symmetry, just by definition. So if we take any permutation from the group Sn, symmetric group, the group of permutation of n elements, then we can associate to it an operator acting in the space of states of multi-particle system, which acts in this way: psi sigma 1, psi sigma n.
Can I ask a question? We consider the system of identical fermions.
Yeah. And fermions. And with the count that the count of antisymmetry for fermionic wave function, this permutation, any such permutation, results in a sign factor, right? So we have -1 to the power modulo sigma psi n, where the sign function, or the privative function, denoted by the modulus of sigma, it takes on two values: 0 if sigma is even permutation, and 1 if sigma is odd, or the sigma is odd. It is quite clear that multiplication of a wave function by sum doesn't change its norm, so this is a unitary transformation, unitary operator. It is also clear that the operator being proportional to the unit operator, even by unit or minus unit, this operator can be used with any Hamiltonian acting in the states of n fermions. So it is a symmetry. So we have a representation, so we get a representation of the symmetric group in the European space of n identical fermions. Any questions?
Yes.
Yeah.
We have a complete set of X1 and Xn, and what part of this set is spins? We can...
It depends on the representation. In some cases we can including the complete set of variables is not unique. Yeah, you may include, for example, for an electron, you can take position coordinates and the z projection of spin, or we can take its momentum, projection of spin, some mixture of both.
But if we have not maybe if we 1 and 2 spin object in this set, we should coincide of all permutation set.
Yes, we deal with n identical fermions. We consider all possible permutations. We have n factorial permutations.
Okay.
But results of each permutation is either plus or minus sign due to the total anti-symmetry of the fermionic wave function. This is one of the postulates of quantum mechanics. Well, actually, the above symmetry transformation, which assigns to each permutation a unitary operator, plus minus 1, these operators form a subgroup in a bigger group. I mean, U1 group, which acts on the states through multiplication by a phase factor. So we can multiply each state psi by a phase factor of psi, where phi is angle variable, the angle variable. Since multiplication by a constant clearly commutes with any operator, this transformation is a symmetry for any Hamiltonian. Yeah? And this symmetry transformation just reflects the inherent ambiguity in describing states by vectors of a complex Hilbert space. So this symmetry, these symmetries have no practical importance. They are present in any theory. There is no interesting or valuable information about the system. More questions? No? Then I think it is a good time to take a 5-minute break. Okay, let us continue the review of our examples. And as a second example, let us consider a free-scale particle. Example 2. A free-scale particle with a Hamiltonian h given by minus h squared over 2m times Laplacian operator.
Excuse me, we consider free?
Yeah, free-scale particle. So the Hamiltonian is given by the kinetic energy, no potential energy. Contribute to the Hamiltonian. So for free particle, the Hamiltonian has this form, and in the absence of external forces acting upon our particle, the three-dimensional physical space looks like homogeneous. So we expect the spatial translation to be symmetries of our Hamiltonian. In the coordinate representation, the translations of the coordinate frame by displacement vector A leads to the following transformation of the wave function. we start with the wave function psi of x. X are Cartesian coordinates, free space. Then we get or define new wave function. A is a displacement vector, which is given by psi x minus a. Notice this minus sign. Why? Why minus? Because if we on shifting the origin of our coordinate system by the vector a, we get new coordinate system. So that the radius vector of the same point x with respect to the new coordinate system, relative to new coordinate system, is x minus a. So in this frame we have the state described by the wave function psi, and in this way psi prime, depending on the new radius vector x minus a. It is clear that this operator, so we take this equality as a definition of our operator u associated to a displacement translation in space by vector a. And it is clear that this operator is linear. Let's check its unitarity. So we consider the norm of the vector u acting on psi. The result is given by the integral of the space with psi x minus a modulus squared, and making this coordinate change, we can write this as integral of psi of x modulus squared, that is psi, the norm of psi squared. So we see that spatial translations preserve the norms of wave functions, as it must be if the operator u is unitary. The operator is unitary. Furthermore, the operator u commutes with the Hamiltonian. Let us check. The Hamiltonian is proportional to the Laplace operator. So we consider the composition of operators u Laplacian times psi of x. By definition of u, I get Laplacian of psi x minus a. So I first differentiate and then shift the argument of the result of differentiation, right? But this is equivalent to the action of the Laplacian to the function x minus a, which can also be written as a composition Laplacian and the symmetry operator u acting upon psi. So we conclude that for any displacement vector A, we have that u of A times h is equal to h u of A. So the operators commute to each other. Now, with the count of unitarity, we can also write that the inverse operator corresponds to the inverse displacement. So this is u of minus a, and is given by the adjoint of the operator U, given by the adjoint operator U. So combine it all together, we can write that U, A, H, U dagger A is equal to H. So this set of operators are Hamiltonian, the Hamiltonian of a free particle. Now it is clear that these spatial translations form a three-dimensional Lie group, which is isomorphic to the vector group, of three-dimensional space. And multiplication law is given by this formula. We apply two translations corresponding to vectors A and B. We get a translation by A plus B, and because addition is commutative, we can also write this as O of B, U of A. So this Lie group is abelian or commutative and is isomorphic to the additive group of three-dimensional vector space. Do you have any questions? Yes, please.
Free-scale particles include as of symmetry group not only transformation.
Which transformation?
Representative.
For free particle?
Yes.
Yes. Yes, of course. And we will consider it as another symmetry transformation of free particle, of course, sure. But before that, let us consider another example. Let us suppose that our particle is exposed to the action of a periodic force or periodic potential. It is not free anymore. Then its Hamiltonian takes the form h squared over m plus n, and we add potential energy V, which is supposed to be periodic in some direction. So V of x plus A is equal to V of x, where A is a fixed displacement vector. It's fixed vector. A typical example of such a situation is an electron moving in a crystal, this cubic lattice, for example. And it is clear that our external potential V breaks homogeneity of the three-dimensional space. So our Hamiltonian is not invariant under arbitrary space translations anymore. The periodicity of the potential, however, implies that invariance under certain space translations still survive. And these are translations of the form Un is given by U n times A, where A is our vector entering the periodicity condition, and n is an arbitrary integer number. I use the above notation for the translation with V. It is clear that all these operators commute with kinetic energy. because kinetic energy is translation invariant, as we have seen. So it remains to show that these operators UN are commute with the potential energy. Let's check. V UN applied to a wave function psi. By definition, it is given by multiplication by the function V of x psi x minus NA. And using the fact that potential V is periodic, I can write this as V of x minus NA psi x minus NA, right? This identity. But then I may continue as UN acting upon V of psi of x. So I can treat this expression as a result of translation acting on the product of functions V and psi. So, combining all together, we conclude that operators UN, family of operators, are operators UN preserve the Hamiltonian.
We consider periodic function of potential energy.
Yeah, we consider periodic potential, yes. Start with periodic potential and consider special translations. We see that the displacement vector is integer multiplier of A. It's not an arbitrary translation. It's a set of very special translations. And it is quite clear that taking together these operators, UN form an infinite cyclic group, which is isomorphic to the additive group of integer numbers. Because we have this multiplication law, UN is equal to what? Right. N plus M. So we have the multiplication law for the group of integer numbers, where multiplication just summations. Okay. As the next example, let us consider the group of spatial rotations. Example 3. Spatial rotations. As we know, each spatial rotation in three-dimensional physical space is defined in Cartesian coordinates by an orthogonal 3×3 matrix. So, applying a rotation to a vector x of three-dimensional space.
Can I ask?
Yeah.
We consider now the free scalar particle.
We don't specify a model at this moment. We just consider some set of transformations, and then we specify models which are invariant under these type of transformations. So we start with another end, with the end of symmetries. And then we consider which Hamiltonians are invariant under these symmetry transformations. So applying rotation, we get u vector x, which is given by the action of an orthogonal operator R on X, so R is the rotation. This means that the matrix R transpose multiplied by R is given by 1, and determinant of R is also 1. Right. Now to each rotation in three-dimensional space there corresponds a unitary transformation in the space of states of a physical system of an arbitrary particle moving in a three-dimensional physical space. In the coordinate representation, we have psi x goes to psi prime x, which may be thought as a result of applying some unitary operator u of r to the original function psi x. And the result is psi of r to the minus 1 power acting upon x. This is a definition of the operator u of r. Definition.
Can I ask, we consider the C functions from Gilbert space, and Gilbert space can be in infinity dimensional.
Yeah, it is infinitely dimensional because
And how coherence with group of three-dimensional rotation?
well, we start with a rotation in three-dimensional space, and into each rotation in three-dimensional space, physical space, we associate some unitary operator u acting in an infinite dimensional Hilbert space by this formula, this just definition. And let us check that these operators u of r do define a unitary representation of the rotation group in the Hilbert space. To this end, consider the action of two successive rotations, R1 and R2. So let us check some rotations, R1, R2 from SO3, and the composition of the corresponding unitary operator applied to the function psi gives us the following expression: u of r2 acting upon psi of r1 to the minus power of x, just by definition of the operator u of r, and applying the second operator u, we get psi r2 to the minus 1, r1 to the minus 1, x. And finally, I can write this as an action of u of r. I can write this also as r1 times r2 to the minus 1 power, x. Remember that inversion interchange operators, right? So the result can be written as u of r2 r1 acting on psi of x. So we see that the assignment r goes to O of r is a representation of the rotation group in the Hilbert space of wave functions of x. Let's verify unitarity. Again, we consider the known of the transformed wave function, or more precisely, the norm squared. This is given by the integral over 3 space of the modulus of r to the minus 1 x modulus squared. And again, making an obvious coordinate change, you can write this integral as integral over the whole space. G-codon of the coordinate change, rotate in the opposite direction. Psi of x modulus squared. And since our transformations are unimodular, it's just one, and we get that is the norm squared of psi. So these transformations are unitary. Now, this transformation, unit transformation, will define a symmetry. We define a symmetry if they correspond, if they leave invariant, leave intact the corresponding Hamiltonian, leave intact the corresponding Hamiltonian, and corresponding Hamiltonian. Now it is easy to see that every Hamiltonian of the form p squared over 2m plus v of the modulus of x is invariant under rotations, under space rotations. With that, u dagger is equal to h for any rotation r. As a more specific example of these Hamiltonians, we can take, for example, the Hamiltonian of free particle where v is just zero, right? Free particle. Another example is a Coulomb potential minus squared over x hydrogen atom, free particle. And as a last example, we can consider three-dimensional isotropic oscillator, for which potential is given by m omega squared over 2 squared. Isotropic oscillator. Okay, questions?
We can consider any spherical symmetric potential.
Yeah. So the point is that V is spherically symmetric because it depends on the length of vector, but not on its direction. So any spherically symmetric potential is rotationally invariant, so the corresponding Hamiltonian has S called P as a subgroup in the full group of its symmetries. Notice that in addition to the rotations, this Hamiltonian is also invariant under space inversions or reflections. I mean the form transformations when x goes to minus x, space inversions. And this transformation also induces a unitary transformation in the Hilbert space of states. psi of x goes to psi of minus x. And this allows us to extend the symmetry group of this Hamiltonian, this O3 group, to the full orthogonal group. So O3 is now a subgroup in a bigger group of symmetries O3, which also includes this inversion. Okay. Questions? Comments? No?
Could you repeat, could you please repeat a little slowly about this?
About these examples,
Yes.
so we see that we have a pretty nice action of the rotation group in the Hilbert space of a particle, which in coordinate representation acts by this rule, right? And now we are interested in Hamiltonians which are invariant under rotations. And the claim was that any Hamiltonian of this form, which is given by the kinetic energy plus potential energy that depends on the module of the modulus of radius vector, of length of radius vector, is invariant under rotation. So for each of such Hamiltonians, SO3 is a part of symmetry group, a subgroup in the symmetry group. And we also see that these Hamiltonians are also invariant under inversions or reflections. So we can extend this symmetry group of rotation to the full orthogonal group. And as particular examples of such Hamiltonians, we can take free particle where we are zero, column potential, which we have considered earlier, and the potential of an isotropic oscillator, which is also given by the length of the radius vector. Okay, let's now consider the last example today. Last example number 4. Example number 4. Consider now an evolution operator. Evolution operator U of t associated to some time-independent Hamiltonian. This is given by the exponential function t over h hat. H is a Hamiltonian system. By definition, each evolution operator defines a one parameter family of unitary operators acting in a Hilbert space of states of our system that lives invariant our Hamiltonian, because U of t h the energy is an integral of motion. Energy integral, so it conserve this time. Therefore, we are led to conclude that the symmetry group of any Hamiltonian, time-independent Hamiltonian, contains a one-parameter subgroup, a trivial one-parameter subgroup associated to the corresponding evolution operator. And this example admits further generalizations. That we are given a conserved quantity A, what's the conserved quantity? The physical quantity, that is a Hermitian operator, which commutes with a Hamiltonian, right? Then we refer to A as a conserved physical quantity. And given such an A, let us consider its exponential function, A, or more precisely, a family of exponential functions. It is clear that this formula defines a one-parameter family of unitary operators if S is a real number. S is a real number. Notice that S, in general, S is a dimensional parameter. It has units, and its physical dimension, by definition, is inverse to the dimension of the quantity A. In the above example, we have S to be equal T over H bar, so the units here is given by joule to the minus power.
Can I ask a question?
Yes.
Now we consider the transformation which conserves the quantity of A.
Yeah, we start with some constant of motion or integral of motion A, and then consider a family of unitary operators which can be defined in this way. For any Hermitian A, U is a unitary operator if S is a real number.
And U conserves the A.
U, my claim is that U is a symmetry of the Hamiltonian. Whenever A is integral of motion. It is quite clear that since A commutes to the Hamiltonian, U, being a function of A, also commutes with the Hamiltonian. So U is a symmetry operator.
Symmetry of Hamiltonian.
Symmetry of our Hamiltonian, that is. For each S, we have and since A and H commute to each other, again we have H.
Can I ask, if U T is when is evolution operator, what is US, what does physical mean?
It depends. Depends on the operator A. Some examples will be considered at the next lecture, right? Now just the general construction, general idea. We start with some. We just try to generalize this example with evolution operator, where we have H Hamiltonian as an argument of the exponential function, but H just one of many integrals of motion, so we replace energy by arbitrary conserved quantity and try to produce some interesting symmetry operators.
It's like from group theory when we have a representation with exponent group.
Yeah, there is some relation with group theory. It has some group theoretical interpretation, but let us focus on physics at the moment. And like the evolution operator, these operators U of S also satisfy some interesting algebraic relations Namely, they form a one-parameter group with respect to the composition. What does it mean? One-parameter group. Well, this means that if we consider composition of u of s and u of t, then using the property of exponential function, already defined that this is given by u of s plus t. It's also clear that u of 0 is given by the unit operator, and again, in view of unitarity, we find that u to the minus 1 of s is given to the adjoint of u, or u of minus s. So we see that to each integral of motion A, we can associate a one-parameter group of symmetries, of the corresponding Hamiltonian. Turns out that the converse statement is also true. If we have some one-parameter group of symmetries of some Hamiltonian, then we can find a conservation laws, an integral of motion which generates this group in this manner, in this fashion. Let us prove this statement. To prove this, we just differentiate this quantity by s. What we get? We get u prime s prime denotes the derivative with respect to s, u of t is equal to u s plus t. Do you agree? I agree. Okay. Now let us put t equals minus s. What?
Line?
Something wrong?
Strich.
Prime?
Prime.
I differentiate with respect to s, so prime acts on the first factor but not on the second one. Now setting t equals minus s, in this expression I get as a consequence that u s is equal to u prime of 0, u of s. Why? Okay. Now let me denote this operator u prime of 0 as I multiplied by a. So let me put by definition I times a. With this definition the last equality takes the form of a differential equation, first order differential equation for the unknown operator u of s, right? For given a, we have some equation with the boundary condition, with the initial condition that u of 0 is equal to 1. And it is quite clear that this equation has a unique solution given by this formula. U of s is given by exponential function of I s times a. I agree.
Yes.
Well, where would define the U prime?
U prime is just, let me write down it explicitly.
Okay.
With respect to the parameter, So starting with the group law, which holds for any one parameter group of transformations, differentiating it, we get that actually this family of operators is generated by some operator A, which is given by the derivative of U evaluated at zero. This is definition of my A. And it remains to check that this A is a Hermitian operator. To call it observable, it should be Hermitian. The Hermicity of A can be deduced from the following sequence of equalities. From the following sequence of equalities. By definition, we have that U dagger S is equal to 1 for any value of the parameter S. Okay? Let us differentiate this quantity by S. Notice that the right hand side doesn't depend on S. Right? So we get U dagger of S primed U of S plus, just by the Leibniz rule, applying the Leibniz rule, we get U dagger of S, U primed S is equal to 0. Right? And now let us put S to 0 in this identity. What we get? What do we get? We get that U dagger of U prime dagger of 0 is equal to minus U hat prime of 0. And if we, so the operator U prime of 0 is anti-Hermitian. The adjoint is given by the operator multiplied by -1. So multiplying this operator by the imaginary unit, we get Hermitian operator. So U prime is anti-Hermitian operator A given by is Hermitian. Is Hermitian. And this operator A is called the generator of a one parameter group of symmetries. Is a generator. One parameter group of symmetries U of S. In such a way, we have proved that to every conserved quantity A, there corresponds a one parameter group of symmetries of the Hamiltonian, and the other way around. Each one parameter group of symmetries is generated by some integral of motion A. So there is one-to-one correspondence between symmetries, parameter groups of symmetries, and the generators. And this statement can be viewed as a quantum mechanical counterpart of the celebrated Noether's theorem, known from classical mechanics, on relationship between symmetries and conservation laws. In classical mechanics, to each one parameter group of or continuous group of symmetries, there corresponds a certain conservation law, and the same is true in quantum mechanics. To each conservation law A, we can associate by making use this formula symmetry transformations, and vice versa. If we have symmetry transformation, it is necessarily generated by some integral function. And at the next lecture, we'll consider some specific examples of such one parameter groups of symmetries. Any questions, please?
For Lie groups, we have Noether theorem in quantum mechanics. I correctly understand. For continuous.
For continuous group, what do we have?
We have Noether theorem in quantum mechanics.
Yeah.
But what with discrete symmetries?
With discrete symmetries, the matter is a bit more complicated. Because, okay, each discrete symmetry is generated by some discrete group of discrete symmetries generated by some unitary operators. Then you can try to, and these operators, all these operators commute with a Hamiltonian. Then you may try to make some Hermitian operators of these unitary operators. There are many ways to do this. For example, you can use this trick with a logarithm if you know that each unitary operator is exponential function of some Hermitian operator A, then we can try to take logarithm of u and define some Hermitian operator. Since A is a function of u, this operator also commutes with a Hamiltonian, so it's integral of motion.
And for A, we can write down the Noether theorem.
Yeah, in principle you may. Another possibility is just take the Hermitian part of this operator, just take u plus u dagger. Clearly this operator is Hermitian, and it commutes with Hamiltonian. It's another way. So there are many ways to associate Hermitian operators to unitary operators. But if you are interested in Noether's theorem, then you, we can think of this construction as a generalization of the Noether's theorem to discrete group quantum mechanics. Discrete groups.
We also can find the set of generators for representation of group.
Discrete group or
discrete group.
No, for discrete group we have no set of generators because there is no parameter here, just a given operator. It is not a family. Of course, you can put some parameter here, but only for special value S you get elements of your discrete group because you are dealing with discrete group, not continuous. There is no continuous parameters in discrete groups.
It means we just need some tricks for proof the Noether theorems for discrete.
Yeah. There's plenty of mathematical tricks here, but The new inversion, quantum version of Noether's theorem concerns continuous groups. Discrete groups are separated. It's quite a bit another story.
Is for field is work for field too?
What?
For fields.
For fields? What do you mean? Fields.
For fields.
In field theory.
In field theory.
Yeah, everything can be
also
translated into field theory.
Okay, in field theory we also have symmetries
Yeah.
and Noether theorem.
Yeah. From this perspective, field theory just a quantum mechanics for a system with infinite or continuous number of degrees of freedom, infinite degrees of freedom, but this is the same quantum mechanics, so we can apply all this construction to field
Because
as well.
there we have the same classical mechanics like with Lagrangian and Hamiltonian formalism.
Yeah, we have.
Is the same?
Yeah, in field theory we can also start with Hamiltonian mechanics, with Hamiltonian for fields, and define a symmetry transformation as those unitary operators which commute with your Hamiltonian.
Hamiltonian.
Yeah, exactly.